Section 4, Section 4.5 talks about derivatives and shapes of the graph. So they talk about if a function is increasing, the derivative is always positive, and if a function is decreasing, the derivative is always negative. So the slope of the tangent is negative all the time. If it's decreasing, again, you move left to right, and if it's increasing, but we did that already. The reason they're bringing this up right here, this is the first time they introduced the line that we've been using to test for f is increasing, decreasing. But that's common sense to us now, hopefully, that we are very comfortable with this. There is another thing that we're going to learn in this section, and that is concavity. Now, whenever you look at a graph, concavity is slightly different than increasing, decreasing. You think of a parabola. If this was a parabola, it should have looked like this. And if this is a parabola, then this parabola should have looked like this. And if this pattern continues, then you would know that, wait a minute, then this will continue down, and again, if this is a parabola, so it should look like that. So you try to make it symmetrical parabolas always, and you're trying to eyeball. If I was taking the path left to right, I am along the yellow. Where do you think I will switch from the yellow and get on to the blue? Somewhere around there. That is where that's what we call inflection points. And that's where the second derivative equals 0, or the second derivative does not exist, provided the value is in the domain. And if I was going along the blue path, and later on I'm going to be along the yellow path, well, again, you got to eyeball kind of like where would that switch from going along the blue to the yellow, and that we call an inflection point. And that's what we're going to try to find. And again, that's where the second derivative equals 0, the second derivative does not exist. Now, if the second derivative is positive, we call the graph concaving up. The graph looks like this, like the yellow shape. And if the second derivative is negative, we say the graph is concaving down, like the blue, like that's concaving down. And we notice here it's concaving up. An inflection point only happens when you switch from concaving up to concaving down, or vice versa. Concaving down, then you concave up. Kind of like you only have a maximum. If f was increasing, then it decreases, right? That's a maximum. And you only have a minimum if f was decreasing, then it increased. So we're going to do the same exact test. Basically, we're going to put the number line, pick test points, and figure out, not the first derivative though, the second derivative, to figure out where the graph is concaving up and concaving down. Now, this point is crucial in the sense, if I was driving up this hill, if I was standing straight right there, if this is a car and I'm looking at the front cover of my car, let's say the center of the front hood, as I go up, I notice the car will be pointing upwards. Now, when I get to that point, that's when I notice the car now is starting to level off until I get to a complete stop. That point, you're still going up, but you're no longer feeling the steepness of the hill. Similarly, if I was standing on top of a hill and I want to drive down, if I look at the front tip of my car, I'll notice that it'll start moving downwards, and I'm feeling the pressure as I drive further and further. So it's still pointing downwards. When I get to that point, I notice that, wait a minute, it's no longer pointing downwards. It's kind of leveling off. And that makes sense because you're going to get to a complete stop. That point is when you stop feeling the pressure that you're really being pulled down, kind of like you're leveling off. And it's a very crucial point. In many applications, they teach their students how to memorize where it is by a formula, like calculus for life sciences and calculus for business and economics. That's what we do. They don't know as much calculus. We say, look, this is what that formula is, and use it and go from there. Now, We're going to start first with a graph. Find the intervals for the following to analyze the graph of f prime. This is f prime. To figure out where is f increasing and decreasing, where do you have a maximum or a minimum? So this is the graph of a derivative. Okay, well, find where a function is increasing and decreasing. In this case, this is the graph of the derivative. This is not the graph of f, this is f prime. So if I get to my traditional testing, so again, if this was the graph of f, I would have said the slope of the tangent, the derivative will be 0 there, 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 and there, but that's not the case. This is the graph of the derivative. Since it is the graph of the derivative equals 0 at -2, at 1, at 0, and 1 again. To the left, this is where the graph of the derivative is negative. So it's negative here, it's negative to the left of 0, and it's negative between 0 and 1. And if the derivative is negative, we know that the function is decreasing. And the graph here, this is the derivative again, up there, it's positive here, here, and to the right. And we know if it's positive, it's increasing. So we could pretty much figure out what's needed. Part A says, remember again, increasing, decreasing, B, local maximum, local minimum. F is increasing from -2 to 1, union with 1 to 0, union with 1 to infinity. And F is decreasing from -infinity to -2, union with 0 to 1. Yeah, okay. And that means we have a local max at x equals 0, and we have a local min at x equal -2 and 1. All right. Now, if I look at the second problem, the same idea. I come in and say, well, all right, let's see how this plays. This is the graph of the derivative again. Where does the derivative equal 0? At -1 and at 1. And it doesn't exist at 0, right? These are the critical numbers. You notice that's a cusp. And what do we know? Wait, if f has a cusp, the derivative has a cusp that doesn't count. If f has a cusp, the derivative does not exist. Okay, well, do you notice the graph is always above the x-axis, which means it's always positive, right? If the derivative is always positive, then the function is increasing, increasing, and increasing. F is increasing from -infinity to -1, union with -1 to 1, union with 1 to infinity. And that means it's decreasing nowhere, obviously, if it's increasing the entire domain. That means we have no local extreme values, extrema, or extremum. No local maximum, no local minimum. Now, that was a special case. Okay, here's another one. And here we would like to take the same as before. We just draw the line and pretty much predict the same predictions. Where does the derivative equal 0? It seems to be 0 at -2. It's 0 at -1, it's 0 at 0. And the graph is negative, f prime is negative below the line, and it's positive above that line. So f prime is negative between -2 and -1, and it's positive, and the rest, that means f was decreasing, then increasing some more. State that f is decreasing from -2, not negative infinity, because start at -2, all the way to -1. F is increasing from -1 to 0, union with 0 all the way to infinity. B, we have a local min at x equal -1, and that's about it. There's no local maximum. Here again we have another special case. If I look at this graph of derivative, I notice that the graph is always above the x-axis. That means the graph is always positive. If the derivative is always positive, the function is always increasing. Therefore, we say f is increasing from -infinity to positive infinity. That's A. It's decreasing nowhere. And B, we have no local max or min, or no extreme values, no extrema. And the last example I have would be this problem. Again, I want to make sure we see that. This is the derivative. So again, since this is the graph of, let me make sure it is, yeah, it is the derivative. Since it is the graph of the derivative, we say, all right, well, where does it equal 0? It equals 0 at -1, it equals 0 at 0, and it equals 0 at 1. We notice the graph is negative below, and it's positive on all of these intervals. And if the graph is, if f prime is negative, the function is decreasing. If it's positive, it's increasing. And that's pretty much what we have to state. And f is increasing from -1 to 0, union with 0 to 1, union with 1 to infinity. And f is decreasing from -infinity to -1. And we have a local minimum, that's A. We have a local minimum at x equal -1. And that's pretty much it for these types of problems. Let me shift a few things around. And here is the official definition that says, well, test for concavity. Let f be a function that is twice differentiable on some interval I. If the second derivative is positive, then we say f is concaving up. And if the second derivative is negative on some pieces of that interval, we say f is concaving down. Kind of like the first derivative test. We do exactly what we did with the first derivative test, but we do it with the second derivative. We do the testing, and we figure out where those happen. And that's how this plays. Now, if you switch from concaving up to concaving down, or concaving down to concaving up, that's called an inflection point. And that's what this is stating. If f is continuous at A, so it has to be continuous at that point for it to be an inflection point, otherwise it doesn't count, and we'll talk about that when we get there. We did that example in the very beginning, but let's look at this function. If I wanted to eyeball visually where the maximums and minimum, the inflection points happened, I'll be thinking of parabolas. If I want it to be symmetric, the parabola should have looked something like this. And if this is a parabola, it should have looked like this. And if this is a parabola, it should have looked like this. And if this is a parabola, it should look like this. So again, you're eyeballing, when do you switch from the yellow to the blue? It seems to be somewhere in there. That's an inflection point, because it was the yellow was concaving down, the blue is concaving up. And if you take that path, again, left to right always, at that point, instead of continuing on this blue, which doesn't exist, you're going to go on the green. That's an inflection point as well. And you're supposed to continue on the green, so the graph should look something like this. But then you're going to switch to the pink, and that's an inflection point. So again, it's kind of hard to eyeball. It's not like where you have a maximum or a minimum. That's not the case. And here we're going to start with a graph, but now be careful what they're asking. They say you're given the graph of f prime, list all inflection points, and where's the graph concaving up or down. Now, to us, this is the idea. This is f prime. I'm trying to figure out where f double prime is doing. So remember when we had f and we did the derivative? Since we're figuring out the rate of change of that, we're no longer looking where f prime is positive or negative. We're pretty much trying to figure out the slope of the tangent at these points. And why is that? Because I'm trying to figure out the rate of change of that. That's what the second derivative is. The rate of change of the first derivative. First, I notice there's a minimum there. So the slope of the tangent has to be 0 there, right? To the left, it seems the slope of the tangent is negative. To the right, the slope of the tangent is positive. If the slope of the tangent is negative, if the second derivative is negative, the function is concaving down, and if it's positive, it's concaving up. And what did they want? They want to know list all inflection points and where they. Okay, so I need a bit more space. So we say f is concaving down from negative infinity to 0, and f is concaving up from 0 all the way to infinity. And we're going to do the same on this problem. Let's do that. I'll put a number line right there, and again, this is what we're going to use all the time. Remember, this is the graph of f prime. The derivative of that is the slope of the tangent. The slope of the tangent will be 0 there and there. Oh, and I forgot here. We have an inflection point at x equals 0 because you switch from concaving up to concaving down. If I look at this graph, to the left of this, isn't the slope of the tangent, the rate of change of that, negative, positive? And if you move between 0 and 1, isn't the slope of that line, tangent line, which is the second derivative, negative? And to the right of that, isn't that positive? If the second derivative is positive, the function is concaving up, and if it's negative, you're concaving down, and that's pretty much it. We say, well, f is concaving up from negative infinity to 0 union with 1 to infinity. F is concaving down from 0 to 1, and we have inflection points at x equal 0 and 1 because you switch from concaving up to concaving down and concaving down to concaving up at that point. Now, here they're telling you that, to figure out where you could have possible inflection points, you take a second derivative set equal to 0 and go from there. If the second derivative is positive, you have a minimum, maximum. This is a second derivative test for a minimum or maximum. We'll come back to that. We're not getting into that for now. For now, let's just follow on what we're doing. This is a function. Tell me where do you have a function increasing or decreasing. Tell me you have a maximum or minimum. Tell me where it is concaving up or down, and tell me where's the inflection point. Well, luckily this is a graph we know. This is x into x minus 6, and it's a parallel that opens up, so it looks something like that. If I'm getting this correctly, there is one minimum and decreasing to the left, increasing to the right, and it seems the graph is concaving upwards all the time. Again, the graph gives you the answer, but the algebra is really how you show it. Well, let's do the first derivative test. Take a derivative, that's 2x minus 6. Where does the derivative equal 0? Where does it not exist? F prime equals 0 when 2x minus 6 equals 0 and x equal 3. And if I do my testing, there's 3 f prime f. Polynomials are the smoothest and most straightforward out of what we do. Pick a point to the left of 3, say 0. You put a 0 in there, that will be negative. Put a point to the right of 3, say 4. You put a 4 in there, 8 minus 2 is positive. So as suspected, f is decreasing from negative infinity to 3. F is increasing from 3 to infinity. and we have a local minimum. This is A, this is B. We have a local minimum, so let me just move this down here, move this up there, and move the conclusion to the right. There it is. And we have a local minimum at x equal 3. Of course, you could plug it in and get 9 minus 18, negative 9. There we go. So I know where that point is. That's the first derivative test. Now for the second derivative test, and this is why you really need to get the product rule, the quotient rule out of the way, because if the first derivative is wrong, the second derivative automatically is wrong. The second derivative will be 2. So where does that equal 0? Where's it undefined? F double prime equals 0 nowhere. I'll do my testing still. There's the second derivative. There's f. Pick any point you want. Let's say pick 1. The second derivative is positive. If the second derivative is positive, f is concaving up from negative infinity to infinity. And that means there are no inflection points. For inflection points to happen, you must switch from concaving up to concaving down, or vice versa. And there it is. Here's another problem. We want to find again, where's the function increasing, decreasing. Again, we know what the graph of that look like. We know that if you take x cubed into x minus 6, the graph will look something like 0, and at 6, you have a multiplicity 3, so this is x to the 4th. It points in opposite direction. These are the intercepts. So since that's a multiplicity 1, the graph looks like this. But here, at this 0, it's going to look like a cubic, so the graph looks something like this. And we could tell that this is concaving down, up, this is concaving down, and then it concaves up again. Well, we have to show that. So the derivative is 4x cubed minus 18x squared, and we want to know where does that equal to 0. That is 1/4 x squared, not 4, 2. 4 doesn't divide 18. 2x squared into 2x minus 9 equal to 0. So that's when x equals 0 and x equal 9 halves. So if I do my testing, there is 0, there's 9 halves, there's the derivative, there's f. If I pick a point to the left of 0, say negative 1, when you square it, it becomes a positive. And negative 2 minus 9 is negative. Positive times a negative is a negative. A point between 0 and 9 halves, say 1. Put a 1 in there, that's always positive. 1 in there, 2 minus 9 is negative. That's also negative. A point to the right of 4.5, say 5. That's positive. And if you put a 5 in there, 10 minus 9 is positive. So we get, okay, I gotta do that a bit better than that. There we go. So we know that from the first derivative that f is decreasing from negative infinity to 0 union with 0 to 9 halves, and f is increasing from 9 halves all the way to infinity. That's A. B. We know that we have a local minimum at x equal 9 halves. We could plug that in and figure out what the y is. That's this point specifically. That's a minimum. Now we're going to do the same, but for the second derivative test, well, we take another derivative of that. F double prime will be 12x squared minus 36x, and we're going to do the same thing. We're going to say, where does that equal 0 or undefined, but it's defined everywhere. We could factor 12x out, x minus 3. So we get x equals 0 or 3, and if we do the testing, there's 0, there's 3, there's f double prime. A point to the left, say negative 1, that's going to be negative, and negative 1 minus 3 is negative, so that's a positive. Between 0 and 3, let's say 2. 12 times 2 is positive, and 2 minus 3 is negative. And a point to the right of 3, say 4, we'll get a positive and a positive. So if the second derivative is positive, the function is concaving up, or the graph concaving down, concaving up. We know that f is concaving down from negative infinity to 0 union with 3 to infinity, and we know that f is concaving up from 0 to 3, concaving up from, oh, I messed up big time. I swapped those. F is concaving up on those and it's concaving down, and we have inflection points at 0 and at 3. And as we see, 0 is an inflection point, and this is 4.5, the minimum. So 3 is about right there, somewhere down there. Now we're not asked to graph, but that's what really is the goal of this. Alright. The following problem, we want to figure out the derivative. That's 1 plus the cosine of 2x times 2. So I want to know, where does that equal? 0. That's when the cosine of 2x equal negative 1/2. Well, that's a reference angle of pi over 3. And cosine is negative in quadrants 2 and 3. So that would be 2 pi over 3, or 4 pi over 3, plus 2 pi k, then limiting the domain. So if I set the angle, which is 2x, equal to that, I'll get x to equal, okay, plus 2 pi k plus 2 pi k. If I multiply by a half, x will be pi over 3 plus pi k, or 2 pi over 3 plus pi k. So since I want those solutions, I let k equal 0. I get x equal pi over 3 from the first. Now from the second, I'll get 2 pi over 3, that's too big. K equal 1 is not going to work, but if I let k equal negative 1, I'll get x equal negative 2 pi over 3, that's not allowed. Or if I take negative pi plus 2 pi over 3, that will be negative pi over 3. So I have 2 points to test. I have negative pi over 3 to play with and pi over 3. There is my derivative. There's my f. I pick a point to the left of negative pi over 3. Let's say negative pi over 2. If you put negative pi over 2 in the derivative, 2 times that is negative pi. Cosine of negative pi is negative 1. No, negative 2 plus 1 is negative. A point between negative and a positive 0. Cosine of 0 is 1 times 2. That's 2 plus 1. That's 3. That's positive. And a point to the right of pi over 3, say pi over 2 as a test point. If you put pi over 2 in there, 2 times that is pi. Cosine of pi is negative 1. Negative 2 plus 1 is negative. So here we are. We know that A, f is decreasing from negative, it should be negative pi over 2 to negative pi over 3, union with pi over 3 to pi over 2, because again, they cut off the restriction between pi over 2 and negative pi over 2. We know that f is increasing from negative pi over 3 to pi over 3. Part B, we know we have a local minimum at x equal negative pi over 3. Again, I could make that a point, plug it in. And we have a local maximum at x equal pi over 3. So that takes care of the first derivative test. Now for the second derivative test, I need to take a derivative of this. If I take a second derivative, that will be 0. Derivative of cosine is negative the sine of 2x times 2, and there's a 2 up front, so that's negative 4 the sine of 2x altogether. And if I set that equal to 0, that's when the sine of 2x equal to 0, and the same game is played. we know that this is a special case. It's 0 at 0 plus pi k, so you let 2x equal that, so x would equal pi over 2k. If you let k equal 0, you get x equals 0. That's accepted. If you let x equal k equal 1 or negative 1, you get pi over 2 and negative pi over 2, but these are the endpoints. So 0 is the only point in this interval that I'm interested in. And there's f double prime and there's f. If I pick a point to the left, let's say negative pi over 4. If I put pi over 4 in there, 2 times pi over 4 is negative pi over 2. Sine of negative pi over 2 is negative 1 times a negative. That's a positive. And if I pick pi over 4 in there, I put pi over 4 in there, 2 times pi over 4 is pi over 2. Sine of pi over 2 is 1 times negative 4. That's a negative. So this is concaving up, concaving down, and that's my conclusion for C and D. C, I would say f is concaving up from negative pi over 2 to 0. F is concaving down from 0 to pi over 2. And D, we have an inflection point at x equals 0. And again, you can plug that into the original and figure out that it's at the origin. And that's pretty much it for those. Now, if you want to talk about the graph of this, well, we could tell at negative pi over 2, that will be negative pi over 2. The sine, 2, that's a 0. So negative pi over 2, negative pi over 2 is negative 1.57. So roughly you're starting right there. And at pi over 2, that's going to be at 1.57, roughly up there. So what's happening between those? We know that there is a minimum at negative pi over 3. Let's say that's negative pi over 3. We have a minimum and a maximum right there. And we could figure out exactly where that point happens if we really want to. If we plug in negative pi over 3, you could plug it in and approximate what that is. That's negative pi over 3 plus the sine of negative 2 pi over 3. Sine of negative 2 pi over 3 is negative. So the point is down here somewhere. And a maximum at pi over 3. If you plug pi over 3 in, so here, you're getting negative pi over 3. And sine of pi over 3, that's 60 degrees, that's radical 3 over 2. When you plug in pi over 3, you're going to get pi over 3, which is 3.14 divided by 3. That's a number a bit bigger than 1, just a bit. And you're going to take pi over 3 in there. The sine of 2 pi over 3 in quadrant 1 is positive. It's radical 3 over 2. This is 0.9. This is 1.7. So this is about 2. We have a maximum at 1 point some, and a maximum look like this. And we have an inflection point at 0, 0. And we know the graph is concaving up from negative pi over 2. So to make it concaving up, it starts right there. It has to look like this. And to make it concaving down, you're going to make it look like that. And there it is. That's the graph. Now, the part I didn't pay attention to, the directions, this is for 224 and 226. From 232 and on, they do the same thing, but they add the last portion, sketch a graph of this function. So, same deal here. We would like to figure out, well, x is always bigger than 0, which means you're going to only look to the right of the origin. Well, we take a derivative. Derivative of natural log of x is 1 over x times radical x plus natural log of x times derivative of square root of x is 1 over twice square root of x. So we could get a common denominator here, and that would be 2x. You multiply this by 2 top and bottom, and you multiply this by radical x top and bottom. Now if you clean this up, you could factor a square root of x out. This cancel with that 1/2 time. So my derivative at the end is 2 plus natural log of x divided by twice radical x. Now, when I say where does my derivative equal 0, you say that's when 2 plus natural log of x equals 0, or natural log of x equal -2. So x will equal e to the -2, which is 1 over e. So that's like 1 over 2.71. That's about 0.5 or a bit less. Well, for testing purposes, and of course, where does the derivative not exist? And that happens when the denominator equals 0, that's when x equals 0. So 0, there's nothing to the left. I'm going to test 1 over e or e to the -2. It doesn't matter, however you want to see this. We want to pick a point to the left of that. Let's say we picked half of that. So e to the -2 multiplied by half of it. That's at this point to the left. I'm looking at the derivative. If I plug that in there, the denominator is positive. For the top, 2 plus natural log of e to the -2 divided by 2 would be 2 plus natural log of e to the -2 minus natural log of 2. This undo each other, and you're left with negative natural log of 2, which is negative. Negative over a positive is a negative. Function is decreasing. And if I take a point to the right, say twice e to the -2, the denominator again will be positive because square root is of a positive quantity is positive. 2 plus natural log of 2 e to the -2. That will be 2 plus natural log of 2 plus natural log of e to the -2. That will be 2 plus natural log of 2 minus 2. The 2's cancel out. I'm left with positive natural log of 2, so that's positive. So we know that f is decreasing from 0 to 1 over e, and f is increasing from 1 over e to infinity. And this is A. B, we know we have a local minimum at 1 over e, or e to the -1, I should say. If I plug that in, I'm looking, and the reason I'm plugging that in because I just realized I need to graph this. I'll take natural log of e to the -1, the square root of 1 over e, that's a -1. So that's -1 divided by square root of e. -1 divided by square root of 2. That's about 0.6. So I know I have a minimum at about -0.6, 0. Something like that. Well, there's the first derivative test. Now the second derivative test, I'm going to pick up where I left off. I'll take a derivative of this. Derivative of the top will be 1 over x times the denominator minus the top times derivative of the denominator. Leave the 2 out. Derivative of a square root is 1 over twice the square root of x. The 2's cancel out. So f double prime will equal. Now I could really say this cancel with half of that. And the problem looks like 2 over radical x minus 2 plus natural log of x over radical x, and they match. This way, that saves me time to say that is over radical x, 2 minus natural log of x. Those cancel out. So my derivative would be negative natural log of x divided by radical x. Now, I want to figure out the same deal. Where is f double prime equals 0? Does not exist. Well, it equals 0 when negative natural log of x equals 0, or natural log of x equals 0, e to the 0, which means x equal 1, and does not exist when x equals 0. We're already aware of that. 0, nothing to the left. Second derivative, 1. If I pick a point to the left of that, let's say I pick, this is 1. If I pick 1 over e, which is e to the -1, the denominator is positive. And if I put that in there, negative natural log of e to the negative 1 is minus a negative 1, that's a positive 1. And if I pick a point to the right of that, say e, I put e in there, the denominator is positive, and if I put e in there, they cancel out, I'm left with a negative 1. So f is concaving up from 0 to 1, and f is concaving down from 1 to infinity. That's part C. And part D, we have an inflection point at 1, and if I put 1 in the original problem, I'll notice that natural log of 1 is 0. Now if I want to put those on a graph, again, because we are supposed to graph this, I overlooked the directions. If I want to look at a graph, 1, 0 is an inflection point. I have a minimum at 1 over e and a negative. This is 1 over e negative, a minimum let me make sure. Yeah, we have a minimum at that. Now at 0, we are at 0. Actually, 0 is an asymptote. And we have concaving down, and the function is decreasing. So concaving down, let me see, something's not adding up for some reason. Oh yeah, that is a minimum, and a minimum looks like this. So concaving down, it's 0 is an asymptote, not an intercept. So open circle, it's going to come down, and then instead of continuing up, it's going to concave downwards. But is it increasing or decreasing? It is increasing. It's going to concave down, so the graph, instead of looking like this, it's going to really look like this. That's what concaving down means. And there it is. And the difference, of course, if it's concaving down, it's going to level off next to a number. Last example we have the following. So in this case, we know the domain 1 is not in the domain, so that's the only value I can't have. I start off with the first derivative. That's derivative of the top times the denominator minus the top times derivative of the denominator all over the denominator squared. And that will be x minus 1 minus x over x minus 1 squared, or simply negative 1 over x minus 1 squared. So if I run the test, f prime equals 0, a fraction equals 0 when the top equals 0, that never happened. Where's f prime not exist? That's when the denominator equals 0 at 1. If I test 1, there's a derivative, there's f. Pick a point to the left of 1, say 0. The top is negative. The denominator, negative 1 squared, is positive. Pick a point to the right of 1, say 2. That's negative. And if I put a 2 in there, 2 minus 1 is 1 squared, that's positive. So it seems the function is decreasing, then decreasing. F is decreasing from negative infinity to negative 1 to 1. Union with 1 to infinity. Well, if a function is always decreasing, then we know that f is increasing nowhere. And we have no extreme values, no local max or min. And again here, the denominator is always square root is positive. Negative divided by positive is always negative. I really didn't need to do the test points, but in case you don't see that, that's okay. Now I want to take the second derivative test, and if I take f double prime, I'm going to treat this as negative x minus 1 to the negative 2. I'm going to bring the power down, subtract 1 from the power. So this is 2 divided by x minus 1 cubed.
And if I do the testing, where's f double prime equals 0, where's f double prime not exist? Again, a fraction equals 0 if the top equals 0, that never happened. Doesn't exist when x equal 1 one more time. If I pick a point to the left of 1, say I picked 0, top is positive, negative 1 cubed is negative, so positive divided by a negative is negative, and if I pick 2, top is positive, denominator 2 minus 1 is positive, so we know that C, f is concave up from 1 to infinity, and f is concave down from negative infinity to 1, and that means D, we have an inflection point at 1. If I plug 1 in, it'll be undefined, so we don't have an inflection point. Now if I want to sketch a rough graph of this, I have a vertical asymptote at x equal 1, horizontal asymptote y equal 1. When x equals 0, y equals 0. The graph is concaving down and then concaving up. And it's always decreasing, as you see, and that's why we have no local extreme values. And that's pretty much it for this section.